I've just installed this new Enviolo Sportive model on my bike, and now it's time to get the automatic shifter programmed so that it will work nicely with it. There's my direct drive hub interface. First thing I need to do is get the end stops on the servo correct so that they match up with the end stops inside the hub itself. To do that, I've connected into the servo's internal potentiometer and feeding that into this Arduino, which is programmed to accept a servo value straight from Bluetooth, and I'll show you on the screen the calibration procedure now. The voltage from the servo's internal potentiometer has been mapped so that it equals the value that I'm sending for the PWM to control the servo. The difference between the two is then the error in the position. If it's plus or minus 2, then it means the servo is able to position itself where it wants to be. As you'll see in a minute, if I send it a value, and the 21 means there's an error. If I send it again, it had time to position itself, and there it's 0. Now let's see if we can find the underdrive end. I send it a 0, and then it's got a small error. Still got an error, so we're too far into underdrive. So if I change that to, say, try a 4, and it's perfect. So that's that end. So I know if I give it a value of 3 or 4 is fine for underdrive. Now let's go up to the other end. Let's try 180. Still okay. Let's see if it will go 190. No, it's got an error. Try again. Big error. There you go. Let's go back to 185. Still got a bit of an error. Back to 180. Yeah, 180. So I think I'll set it to probably 5 to 180 for that. It's then time to take the bike for a ride and get some data. This is the best way to do it because the hub's ratio is somewhat dependent on the torque going through it. When we get back from the ride, we have the data, which is this here, 16,000 lines of it. From that, we calculate the real servo position in this column here, and then the hub ratio in the big ring and the small ring, using the derailleur position there, and then combined together into this column here. So then these two columns here are the ones of interest, which we then analyze. They're plotted on this graph. The orange is the data, and then using a method that I learnt for wind turbine power curves, we average the ratio for each bin, as it's known. This is the lower bound and upper bound for each of the bins, and we then ask the spreadsheet with this equation here to find the average for each bin, and that's this blue line plotted here. From that we then have basically the hub ratio for a given servo position. From now on I'll be using the old servo position values, which is basically the PWM time, milliseconds, rather than the angle in degrees. So that then goes on to here, which we then calculate the speed for a given servo position if the input RPM is this, and then that's these here on the graph for the small ring and the big ring. This line is then the calculated servo position for a given speed using the equation in the automatic shifter, which has these values here we can change, and we can configure that equation so that this blue line will line up with these lines here. So starting at 50 RPM, we need to then change this value here to get the right gradient, which is, I already know that one, be 30, and then get the offset right, which will be a bit more, 100, the offset, and then this one here is a value depends on the chain rings, how many teeth are on the chain ring and the sprocket. So this will be for the big chain ring, or if we put 16 in, small chain ring, and you see it moves to there. If I change the chain ring size, then I'd have to change that value there. So then we have to basically go through for each cadence setting and find the optimum multiplier. The offset will remain the same, this offset. That just depends on the orientation of the hub interface. If that changes, then you can change that to compensate for it. So that's fine. We've got this here, basically that's the multiplier for a given cadence setting. But if we want to then use the power meter, so we then want to change the multiplier depending on the power. At the moment I'm just using a basic linear relationship between them, which is basically this here. That's the multiplier required to get the basic cadence. That's this line plotted here, this one. We then obviously need to find an equation, which is this one here, which calculates the multiplier for a given power, and that has to be then fitted. So that's what we want to get, and yeah, so that's what we calculated using that equation, and that's the optimum if we want a straight line. Of course, we can fiddle with this and change it. If I bring this graph up here, I can show you can change the relationship between power and cadence by changing these two values here. Change that to say 10 and that to 20. We then have, say, someone who likes to pedal a lot faster. We would have different equation. We can change this to say something like that. So that would start off at a higher RPM at low power, but then wouldn't be so fast as the power increases. So it'd be less effect. The power meter will have less effect. And you can basically, these two values can be changed by, say, buttons on the handlebars, for example, to modify the way it behaves, depending on the power. And that explains it all of the calculations involved and the automatic shifter. And yeah, thank you for watching.